Okay, so in this video, I want to talk about the Cobb-Douglas preferences. So we've been working on consumer theory, and our general problem is we're looking for two arguments, x and y, that maximize the utility function subject to a budget constraint. And our utility function for this video is going to take a nice form that looks like this: x to the half, y to the half. And more generally, a Cobb-Douglas utility function can take a few forms. Here's a general form: x to the power of alpha, y to the power beta, and I can have a constant in front. Right? Because utility functions are ordinal, right? So they're trying just to order different preferences. Any monotonic transformation, so for example, if I take a log of this or a natural log of this, then I'll have something like ln of a plus alpha ln of x plus beta ln of y is a transformation of that utility function. It represents the same preferences. What does it mean to represent the same preferences? Well, it simply means that the indifference curves are going to look identical. So if you try and draw indifference curve of this utility function or the ln of the utility function, the numerical values of each indifferent curve, of each indifference curve is going to be different, but the visual of those indifference curves is going to be exactly the same. Okay, and my favorite way for this, Cobb-Douglas is one of the most widely used functional forms in economics. And I would like you to know that if you see something very general, say for example, let me give you the most general Cobb-Douglas form that you could see. So the most general Cobb-Douglas form would look something like this: x to the power of alpha, y to the power of beta, and we'll have some general pricing px and py. And what I'd like to convince you on this video is the mechanics of this. I would like my students to be able to immediately see that the solution to Cobb-Douglas is that x star, this argument that you're looking for, is alpha over alpha plus beta of the money are spent on x. And y star, if you could make an educated guess, what would that be? Beta over alpha plus beta times m over py. Think about the intuition of this for a second, okay? This number here is going to be a number between 0 and 1, right? Because it's a fraction. So this alpha shows up both in the numerator and the denominator. Alpha and beta we're going to assume to be positives, okay? So this is a fraction. This is the complementary of that fraction, okay? Or if I sum these two together, they sum to 1, okay? So if I multiply this fraction by the money, is the fraction of the money that I'm going to spend on good X, right? How many units of good X will I get? Well, I'm going to have to divide that amount of money that I'm going to spend on it by X. So the Cobb-Douglas is telling us something quite intuitive, which is I'm going to spend a constant fraction of my income on each good regardless of the prices. Okay, an intuition on this would be to look at something like food and shelter, right? When someone might spend maybe half of their income on food and half of their income on shelter, right? Broadly speaking, right? So that's really what we're trying to show. Note that if any of this is zero, then the utility is zero. That cannot really be a maximum. So we're going to have both of those x and y. So we're going to have a corner. We're going to have an interior solution. We're not going to have a corner solution. And if I look at the indifference curves of Cobb-Douglas, they're going to asymptote on the x and the y. Okay, so they're never going to touch the x and the y, which means if I have some budget constraint, it doesn't matter how steep that budget constraint is. I could be here, or I could be here. I'm going to find a nice, smooth tangency with the budget constraint. Okay, so one way to solve for the Cobb-Douglas is to effectively say, aha, because I have an interior solution, I'm going to have this nice tangency between the budget. What's the slope of the budget? In the previous videos, we said that the absolute value of the slope of the budget is px over py. Okay, that's the slope of the budget. The slope of the budget must equal to the slope of the indifference curve. But what is the slope of the indifference curve in absolute value? Margin utility of x over margin utility of y. So if you take a standard Cobb-Douglas, and you do a marginal utility of x. Okay, so I'm going to treat x as the variable, y as a constant. So I'm going to have alpha x, alpha minus 1, y to the power of beta. That's the marginal utility with respect to x. Marginal utility with respect to y, I'm going to treat the x to the power of alpha as just a constant. So constant times beta y beta minus 1. Okay, and what you can see here is that this x here will cancel with this. This bit here will cancel with this. If you want to flip around the y to the minus 1, send it up to the numerator with a positive, x to the minus 1, send it down with a positive, it's going to look alpha over beta times y over x. Okay, so really there are infinitely many points that satisfy this condition. Makes sense, right? Because there's nothing here. This tells you nothing about the income that I have. So if I have another budget here, I could find another tangency position on a different indifference curve. So it just tells me that there's a tendency, but doesn't tell me where exactly the tendency is. Okay, so there's infinitely many such positions. So one of the conditions that I have in Cobb-Douglas is that px over py is equal to alpha over beta times y over x. Okay, so it tells me there's going to be a tendency. It doesn't tell me where it is. Where's the second condition? So I have two variables, two unknowns, the y and the x, the alpha, the beta, px, py. Here they're just letters, but you're going to know exactly what those numbers are. What's the second one? It's the budget constraint. Px times x py times y is equal to my money. And as a homework, you can try and do this. It's not going to be very difficult to try and express x. So solve this equation through let's say substitution. Okay, so you know what y is here. You plug the y here, get an expression for x. You should convince yourself that x will be equal to alpha over alpha plus beta times m over px. Once you plug it into y, you can convince yourself that this is going to be beta over alpha plus beta times m over py. And if you are in an exam condition, for example, and you know you've derived this once, you can almost skip those steps, right? If you remember this, I advise my students to always remember this formula by heart, right? But also know how to derive it, right? But if you're in an exam condition, you're rushing, you don't have to derive the formula all the time. You could say, using equation 1 and equation 2, making the appropriate algebraic manipulation, we came to x and y. And this is the Cobb-Douglas for you. So if I were to go back to my original question, which was this, and let's say, for example, we had prices of 2, or prices of 4, income of 12. Okay, if you give me this particular Cobb-Douglas with an alpha of a half, a beta of a half, price of x of 2, price of y of 4, income of 12, I know the answers right away. I'm going to spend half of my income on x. Okay, what's half of my income? 6. How many units of x can I get? Well, 6 divided by 2 is 3. So I immediately know that the x star is equal to 3. What about y? Well, I'm going to spend half of my income on y. So 6. What's the price of y? 4. So how many y's am I going to get? 1.5. And I hope this helps. I'll see you on the next video.